We just analyzed the exponential generating function. It is mainly used for handling permutations with repetition. As we said before, full permutation of multisets are permutations where all elements must be used. Then it should be n factorial divided by n1 factorial n2 factorial multiplied down to 1, where n is equal to the sum of all n1, n2s, and rest. So for permutation of repetition, not all the elements are taken out. So how do we deal with these problems? We use the exponential generating function, which we use expressed as GEX. Here, each of the elements have to find its general term, which is x to the kth power divided by k factorial. Therefore, for the first term, the exponential generating function can be written as 1 plus x divided by 1 factorial plus x2 divided by 2 factorial added until x to the n1's power divided by n2 factorial. For the second element and others, the handling process is the same. So in short, we can see that in fact the exponential generating function has some advantages. It can be very intuitive to solve permutations with repetition. Therefore, we will find that we can actually handle problem involve some numerical string now. For example, let's say we have 4 numbers 1, 2, 3, and 4, and this number constitute a 5-digit number, but there are certain requirements. 1 cannot appear more than 2 times, but have to appear for 2. It cannot appear more than once. 3 can appear to 3 times, but can also not appear at all. And 4 must appear an even number of times. When we see this problem, we might think that it is too complicated with so many conditions. But if we use exponential generating function, this problem can be solved directly. So let's take a closer look at this. Even though conditions are very complex, however, if we use generating function, we will find that the question is not too difficult. We assume that AR is a number of R digits which satisfy the constraints. The exponential generating function of the sequence A0, A1 until A10 can be expressed as GEX equals to the generating function corresponding to each number. It has a requirement that it says no more than 2 times. That means the highest term can only be x squared divided by 2 factorial. Pay attention, because this is a permutation, so the general term of general function we use must be divided by k factorial. There is also another requirement, must appear, which expresses that x to the 0th power must not appear in the function. Therefore, it can only appear once or twice. For 2, it says that it can not appear more than once, which means equal to say appear 0 times or once. For 3, the condition is up to 3 times. This means that maximum time it appears 3 could be 0 or 1 or 4. For 4, the condition is appear an even number. We would feel very difficult to express it, but in the generating function, it is very convenient. It should be 0 times, 2 times, or 4 times. On solving the equation, obtained the coefficients corresponding to AR. Then we multiply all the terms. First, solve for the product of first term and the second term, followed by the product of the third and the fourth term, and keep multiplying 2 terms like this. Then multiplying the result. After the multiplication, we see that a corresponding generating function has been generated. But what are the requirements again? We are looking to solve for the coefficient AR. In fact, it should be the number of x raised to r divided by the factorial of r. So we simplify it and write out each term in the form of x raised to k divided by the k factorial. For example, we want to find a 5-digit number. Then we look for the corresponding coefficient in the front of x to the 5th power divided by 5 power. So the answer should be 215. Just now, we looked at how 5-digit numbers use the exponential generating function. But what about for an n-digit number? Let's look at this problem. We have 1, 3, 5, 7, and 9, these 5 digits, and I want to construct an n-digit string. So how many such strings exist? But in these strings, we require that 3 and 7 only appear an even number of times. For the other numbers 1, 5, and 9, we do not have any limitations. So how to solve this question? In fact, according to the requirements, we can directly write out the corresponding exponential generating function. So we have 5 numbers 1, 3, 5, 7, and 9, out of which 7 and 3 has constraint. It says 3 and 7 appears an even number of times. Well, we know that how to write even number of times, which is directly the 0 term, x squared term, and x to the first term summed together. So for 3 and 7, their generating function look like this. For other numbers, there is no constraints, so they are just 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial. So there are 3 digits with 3 constraints, so we can raise it to the third power. This is a corresponding exponential general function. For our question, so we have this, we can further expand it. Since we know the exponential general function where the coefficient equal 1, its general term equals to e to the x. So here, this term can be directly expressed as a e to the x. But how to represent terms before it? How do we get rid of the corresponding odd terms? Let's carefully think about it. You might remember if here we change x to negative x, here it is equivalent to just adding a sign to x. For odd terms, we add a negative sign in front. For even entries, we have positive sign in front. If we add and subtract these two terms, we can eliminate the odd or even terms. Here we can directly know after adding the 2ex and the e to the negative x divided by 2. This way, we naturally eliminated all the odd terms, which leaves only the even terms. So for the generating function of 3 and 7, we can also directly use e to the x power and the e to the minus x. After we get this expression, we can substitute it into the original gex. This is equivalent to the previous one, 1 over 2ex plus e raised to the minus x squared, and then we pull out 1 over 2 and turn it into 1 over 4. Inside, only ex and e to the negative x squared is left for the last term. Because each term equal to the e to the x, the cube of this will equal to e raised to 3x. We now expand this by expanding the square of e to the x and e to the negative x. We will get this expression. Finally, we put e to the 3x product inside and parentheses. Then we get a new answer. 1 over 4 times e to the 5x plus 2 times e 3x plus e to the x corresponding to this e to the 5x. It is equivalent to the sequence that is 5. So we have directly solved the product here. The general term is x raised to n divided by n factorial. Here the coefficient in front is 5, which corresponding to each of the x inside will become 5x. So for x to the nth power in front, it naturally has a 5 to the n. Here it is the same. E raised to 3x is equivalent to the 3 to the nth multiplied by x to the nth power divided by n factorial. Continuing in a similar manner, we can pull out all the coefficients in front of x to the nth power divided by n factorial, which is the coefficients 5 raised to n plus 2 multiplied with 3 to the n plus 1. The general term is x to the nth power divided by n factorial. Of course, do not forget that there is still a 1 over 4. This time the solution is clear at the glance. And an standing for the n-bit string with its constraints. The count of these numbers equal to 1 over 4 times 5 raised to n plus 2 multiplied by 3 to the n plus 1. This is the final answer.